and start recording again. So, now that I started recording again, let me just repeat that. I saw in the lecture it's some more involved description of the math involved in calculating the regression line, calculating the R squared based on the sum of squares of the differences that are due to the regression over the total sum of squares of the differences, and so on. As I said, I won't expect you to know that for the exam, just how to calculate it using SPSS, how to calculate R squared, the significance of what R and R squared are, how to formulate the equation that represents that regression, that linear regression, how to apply it. We're going to work on that right now. We're actually going to do a few examples. So I see a number of you guys are back. Let me just make sure we're all muted here and ready to go. So I'm going to go to a couple of examples, a couple of data files that we have on Blackboard. I'm going to start with this, with one in particular here. Let's see. Let me open up SPSS. So, open data. Here's one. It's baseball season, so this might apply. Slugging percentage is kind of like a batting average. See 0.530, 0.0050, and so on and so forth. Slugging percentage is kind of like a batting average. I think it's got something to do with how many doubles and triples and home runs you hit, and how many RBIs, and so on and so forth. It's not just batting average. And this is a look at the average slugging percentage for each different team and the altitude of the stadium that team plays at. There's a lot of that I don't know how many of you have seen that movie Moneyball, where a team, I think it was Anaheim, Anaheim? That was a team with a relatively low budget for players. They employed a statistician who analyzed the performance of players based on many, many different parameters, and he actually correlated that to the salaries that they were asking for. And he found that there were a lot of players around that were very good performers whose salaries didn't match their level of performance when you really looked at it very carefully from things that really paid off in terms of scoring runs or playing baseball. If you ever get a chance to see it, it's called Moneyball, and it's a pretty interesting picture. And they had a very good year based on, they made it to the playoffs for the first time in a long time. And now this is basically the way most teams select players. They do careful statistical analysis of the player's performances, weigh that against the salary, the cost of the player, and so on and so forth. And it's gotten around the league now. It's not just that one team that was doing it. So at any rate, one of the things that people that are into baseball are into these fantasy leagues. They're into statistics. Every facet of baseball is examined in terms of statistics. Let's take the argument that some people have an argument that teams that play at a higher altitude, like in Denver, may have an advantage because maybe the ball travels further, the air's thinner, ball travels further. Maybe they're at a disadvantage, less oxygen, and so on and so forth. But you might be tempted to see if there's some sort of an association between a couple of numerical variables that involve altitude and some measurement of hitting performance, in this case, slugging percentage. So if we were to examine this, let me open the chat box here in case anybody's saying anything about this. Nobody saw Moneyball, eh? No chat, nobody mentioned anything about that. So at any rate, let's examine this possibility, see if there is an association here. So what do you think the first thing I might do to examine if there's an association? Right? Get a good look at this. Right, let's do a scatter plot and see if there is an association. Okay, now at this point, I don't really care whether the altitude or slugging. We know that the slugging percentage is not going to make a change in altitude. Altitude is altitude. This is going to be the other round, but it really doesn't matter at this point, which I make the y and the x-axis, because I'm only examining it for an association. So let's take a look at what this looks like. Well, let's say, that doesn't look too good there. Maybe it's a little bit more obvious there is one team over here which is way, way out of the range of this whole thing. And I think I should be able to figure out which one that is. Actually, I can do it this way. Okay, I've got a problem. I have an outlier here. Somebody that's a very high altitude that's got an extremely high slugging percentage, much different than the others. And it's really kind of throwing all this data off. Maybe this is based on too small a sample size or something like that. I'm gonna say to myself, let me eliminate that outlier and see how this looks instead. Okay, especially when you have an outlier that's, remember, when we have a line like this, it's almost like a teeter totter, right? Like a balance. Okay, if you have something at the end that's way at the end, it tends to affect the slope of the line much more dramatically than something that's off way in the middle, right? There's someone large in the middle is not going to affect the direction of teeter totter quite as much. So let me go into the data here. And see which one that was. That was a slugging percentage of, that's probably an entry error of 5, an altitude of 5,000, and a slugging percentage of, let's see, I should be able to find it from the altitude. Altitude of 5,000, that's Denver, that's probably that one. I'm going to delete that one. Okay, let me redo this. Graphs, legacy dialogues, scatter dot. Okay, define. Okay, I'm gonna move them around type 2. I think it might be a little easier to see. Let's go back this way. I meant to do it the other way, I think. Okay, let's put altitude in the x-axis, slugging percentage, and y-axis, just make it a little bit more sense. See what this looks like. Wow, this is a little bit more interesting. Does it look like there's a correlation there? Doesn't look like much of one, does it? Little bit, maybe. Let's draw that best fit line and see what that looks like. That least squares line. There's a little bit of a correlation, right? A little bit of an effect. And my R value, what does my R square value look like? Well, gee, it's only 0.03, right? What does that tell us? That tells us that the altitude only accounts for 3 or 4% of the variability in the slugging percentage. So there's a lot of other factors that affect slugging percentage rather than altitude that you're playing at. So this doesn't look like a great correlation. Let me just see. Let me look at this mathematically now. Let's look at that calculation for Pearson's chi-square. Pearson's correlation for R. Correlation, bivariate. Okay, and let's move our two variables in there. And let's calculate that. Okay, let's see what we have here. Well, let's see. Our Pearson's chi-square, the correlation between slugging percentage and altitude is 0.19. It's a lot closer to 0 than it is to 1. So it sure doesn't seem like there's much of a correlation here, right? Besides that, the other thing I see here is that the significance is very low, is very high, right? The p-value, the probability of being wrong if we reject the null hypothesis that the Pearson's correlation is 0 is very high. There's a good chance I'd be wrong in rejecting that null hypothesis. In other words, there doesn't seem, number one, not only is it small, but even that small amount of correlation that I'm looking at there is not supported by statistical significance, right? So maybe this doesn't work out so well for me, right? Let's take a look at another data set. So not every data set is going to be productive in terms of finding a true association, a real association. Okay, so now I'm going to open this data set called BMI and insulin sensitivity. Oh, actually, maybe I should. That's one that we used in the homework, I think. I'm not going to use that one. I'll leave that one for you to work with on the homework. Open data. I'm going to use a different one. I'm going to use violent crime. Okay, I'm okay with the encoding. Okay, let's take a look at what these variables are. Okay, each one of these is different states. I'm going to have a situation where we're going to have to eliminate one of these pieces of data because it's an outlier. Again, I know that going in ahead of time, but we're about to discover that. Okay, so, but I have a good reason for eliminating it. Okay, so let's see what these the variable. This is the state. The state that's a categorical variable. The violent crime rate, the murder rate. These are percentages, I guess, or numbers per thousand or 100,000. We actually might have better description in here. That doesn't really. It would be nice in the label if it gave what the units were there. But we don't have to worry about it. Units. Is not that important to us right now. Okay, but these are all scalar variables. The violent crime rate in each one of these states. Okay, and that's probably number of crimes per 10,000, 100,000 individuals. The murder rate, again, a numerical variable, number of murders per 100,000 individuals. Poverty rate is the percentage of the population that's below the poverty line, the percentage of people that completed high school or college, the percentage of families that have a single parent, the unemployment rate, and a measurement of whether it's a metropolitan or a rural environment, what's largely metropolitan or rural environment that's in that locality. Okay, so I'm going to see if there's an association between a couple of these. So let's see. I'm interested. Let's see how much of the murder rate is associated with poverty, with say single parent homes, with the unemployment rate. Okay, see if there's associations with each of these. So I'm going to take a look at the murder rate. That's one thing I want to compare to the poverty rate. Let's see if we see an association there. Graphs, legacy dialog. I'm going to go into scatter dot. Okay, and again, I'm going to pick simple scatter dot. And I'm going to say, okay, so I'm interested in what will increase, what effect these various factors have on the murder rates. I'm going to move the murder rate in there, and I'm going to start with poverty. Let's move poverty into the x-axis. So let's take a look at the poverty rate and murder rate. Okay, let's see how my graph looks. Wow, look at this. Well, I'm looking down here. It looks like there might be a bit of an association here, doesn't it? Right? This is the percentage of people below the line, poverty line in these different states, and this is the rate of murders in those states. I have an outlier up here, right? There's one that has, let's say this is per 10,000 people or 100,000 people. There's one that has 40 where all these others are so much lower. Let's go back to the data to see which one that is. Anybody want to guess which one that is? What do you think? Uh, Bingo. There you go. One of the states, not all of these are states. There's actually 41 different, 51 different subjects here, 51 different entries here. The District of Columbia had a very high murder rate. Now, one of the reasons there might be, maybe it's just simply there's a higher murder rate, but also the other problem here is that the District of Columbia has a very small population compared to all these other states, to Idaho, to New York, and so on and so forth. So, did that just crash? Did I just crash? I think I did. Yeah, SPSS crashed on me, disappeared. I'll go back to that point. So at any rate, they give me a chance to, while it's booting up, they give me a chance to talk about that. DC has a much smaller population than all these other entries there, which are states. Okay, so even if they had a few extra murders, that would appear to be a much higher rate, just because the population is so small that you're considering it in. So it could be that they have like a much higher rate of murders. That could be a factor, or it could just simply be that and during this particular year or period of time that we're examining this, that they happen to have a few extra murders which are blown up compared to the other ones because of the small population. So I'm going to eliminate DC. Not a state anyway, so I don't feel so bad about clearing that out of here. So I'm going to take another look at this graph. Okay, we'll get an idea of. So I'm interested in predicting violent crime, murder rate based on the rate of poverty. Okay, so click OK. And let's see how we look now that we've eliminated. Well, now it looks a lot more like we have some sort of correlation there, that as the poverty rate goes up, the murder rate goes up as well. Okay, and in fact, I'm going to double click on this and just get a quick look at the best fit line. And indeed, this looks a little bit more encouraging now, doesn't it? It looks like we have an association. Maybe it's not a perfect association, but it looks like we have a bit of an association. So let's analyze this now. Let's go into our statistics. Let me go back to the data set, analyze, correlation by variant. And I'm going to move murder rate and poverty into my variables. And I'm going to go ahead and calculate my Pearson's chi-square. Let's see what we have. Well, our Pearson's correlation comes out to be 0.427. So that's about pretty close to a half. So it's not 0, it's not 1, it's not a perfect correlation, certainly, but it does appear that we have some association between the poverty rate and the murder rate. Okay, and is that statistically significant? Can I toss out the idea that there's no association? In other words, R is equal to 0, that there's no association. Well, yeah, it's less than 0.05. The probability of my being wrong, if I reject that null hypothesis that there's no association and say that there is an association, chances I'm wrong is less than 5%. So I'm going to go ahead and say that there is an association here. Not a perfect one, not a perfect correlation, certainly, but there is one. We know it's positive. As the poverty level goes up, the murder rate tends to go up as well. Okay, so let's give this a try now and look at. Let's see if we can evaluate this association now using regression to really quantify it. See what the slope of the line is. See if we can see quantify how much the poverty rate really impacts the murder rate. So I'm going to go up here to analyze. This time I'm going to go to regression. I'm going to go to linear regression. And I'm going to go, let's see, the dependent variable, the one that is the predicted variable, the one that we're trying to predict is the murder rate. And we're trying to predict it based on the independent variable or the predictor variable, which is poverty. This is the predictor, this is the predicted. This is independent variable, the dependent variable. I'll click OK. Now see what we wind up with here. Again, we calculate the R value, it's 0.427. R squared can be calculated a couple of ways. You saw, if you got through that part of the lecture, you saw that Levi discussed how this is really a measure of how much of the variability is due to the regression and how much of it is due to other stuff, right? And in fact, it comes out to the same thing. It's just squaring the R value, okay? And it comes out to be about 8.18, 18%, right? So our 18% suggests that 18% of the variability in the murder rate is explained by the rate of poverty. Well, that means 80% roughly is explained by other stuff. It could be education level. It could be unemployment levels. It could be many, urbanization. It could be population density. It could be many other things. But at least for these two factors, at least for the poverty level, about 18% of the variability in the murder rate seems to be explained by this one factor, right? That's actually not too bad. So let's take a look at this. Let's take a look at our chart down here, and we take a look at our constant and our poverty level in our coefficients table. Now, what does that tell me? That tells me that if I were going to draw that line, that best fit line, that it would be represented by the formula y. Okay, I'm going to use the notation in the lecture. As I said, So you'll see it as mx plus b in math classes. In most statistical classes, they'll say a plus bx for a is a y-intercept. Levi was using the notation b0 plus bx. Okay, for the y-intercept and the slope value. Okay, so I'll use that. So y is the independent variable. In other words, that's the murder rate. So the murder rate, based on what we've learned from this graph, the murder rate is equal to the y-intercept, which is 0.432. Okay, plus 2 times the slope times what's the independent variable. The slope is 0.365. Whoops. Actually, let me see if I can't undo that. 0.365 plus 0.365 times the value of the poverty level. Okay, that percentage, which represents poverty level. Okay, so that's our formula, which represents our understanding of how the poverty level and the murder rate are associated. So if the poverty level is 1%, then this is going to be 0.365 times 1%, or 0.0365, plus 0.0432. So the murder rate will likely be the sum of those two numbers. Well, can I see that somewhere? Can I see what those values actually are? Well, in fact, I'm going to go back into Analyze. I'm going to go into Regression, Linear Regression. Okay, and this time, notice it's still set up the way it was before. This time I'm going to click on this little box that says Save. And in this box that says Saves, I'm going to click on Predicted Values Unstandardized. And I'm going to look just that for a moment. Then I'm going to click Continue, and I'm going to click OK. Now, SPSS will just repeat the analysis that we just did. The tables look pretty much the same as they did before. There's a little extra table here about residuals statistics. We'll get to that in a second. But the real change here is not in the output table. The real change here, since I clicked that Save button and asked it to save the unstandardized predicted values. Predicted values are the values for murder rate. I'm going to go up here to our data file. And now in our data file, there's an extra column there. And that extra column represents the value that you get for the murder rate if you plug that number into that formula. Some of these, we know they're not going to match up exactly, don't we? Right? We know they're not going to match up exactly because if you look at the chart, let me go back to the output window. If you look at the scatter plot, right, you can see that the line actually only goes through very few points. Most of the points are missed by the line. But the line represents the best guess at what the murder rate would be based on the poverty level. Right? It's not going to be perfect, but it's a way for us to measure it. Okay, so if I go back to my data view, okay, so you can see each one of these predictions on what the murder rate is going to be based on the poverty level. For instance, here it was actually 8, and we only predicted about 5. Here it was 2.9, and we predicted 4.27. 1.6. So a lot of these places doesn't do a great job of it, but there is now it's because it's not a perfect correlation, not that good a correlation, but there is an association here, so that there is some association that we can dig out of this, which gives us an idea of what the association between these two variables is. Now, the other thing I can do when I go into our analysis, Analyze, Regression, Linear. Okay, I'm hoping when we do another one, it's going to come out a little bit better, by the way. Save. I'm going to turn on unstandardized residuals. I'm going to do this again. Unstandardized residuals, you may have noticed that when Levi was talking about the formula, he also added another factor, plus this little E style symbol, right? This little E. Okay, that is the residual for each one of the values that we have measurements for. Well, what does that mean? That means if we plugged in what X is and we plugged in what Y is to the formula, if we plugged in the murder rate and the poverty level, as we did to calculate, our estimated murder rate based on the formula rather than what it was actually for that particular state, well, the difference between what the formula tells us and what it really is called the residual. So if I go back to my data view, oops. If I go back to my data view, my data view. Now you'll see a column here that says residuals, right? And those are the differences between the murder rate based on the formula and the murder rate that actually was experienced in that population. 7.4 minus 7.59 is 1.6. So these are the differences. Notice some of them, in some cases it's overestimated, some cases it's underestimated. Well, if this, what would we expect from these residuals in terms of how would you expect them to be distributed? Anyone has a guess about this? Would we expect the residuals to be bigger for the lower poverty areas or for the higher poverty areas, for the high murder rates, the lower murder rates, and so on and so forth? Well, we would expect these to be basically normally distributed, right? We wouldn't expect that one end of this would have more of an error rate than the other end of it would. So one of the ways that we check on whether or not this is legitimate is to examine how these residuals are distributed. I'll hold off on discussing more about that until Monday when we talk about multiple regression. Let's take a look at another variable. Yeah, we're gonna do this again. Okay, so actually I want to get rid of these, so I just want to clear these out. So we don't get too much stuff in here that's going to confuse us. So let's take a look at another variable. I'll ask you, what do you think is most likely of these other factors to affect the murder rate? Okay, analyze. I'm going to start with a graph. Legacy dialogues, scatter dot. Okay, good. Okay, so which of these variables, I'll take poverty out now. Which of these do you think would be the next one, most likely one to affect the murder rate? Do you think it's the education level, for instance? Do you think it's the percentage of single parent homes? Think it's unemployment rate? What do you think I should try next? Anybody want to take a look at one of these? Hazard a guess? Okay, how about if we look at the unemployment rate next? Okay, let's see how that affects the murder rate. I'm going to click OK. Okay, and again, so it looks like we have a similar kind of correlation here. And so let's take a look at this and let's analyze this now. I'm not going to bother to draw a line now. I'm going to analyze this. Regression linear. Okay, here's my murder rate. Now, instead of poverty rate, now I'm going to be looking at the unemployment rate. Okay, and I'm going to click OK and see what we wind up with. Okay, let's look at our R value for this. Let's see, variables. Here we go. Our R value is 0.351. R squared is 0.12. So only 12% of the variability of murder rate can be attributed to the unemployment rate. So this doesn't look to be as good a predictor of the unemployment rate as a murder rate as poverty was. Interesting, right? So we have a measure of one thing being not quite as good a predictor of murder rate. And if I look at this, I can see my formula is going to represent let's see, the constant is 0.972. That's where it crosses the y-axis, right? So that I need to get my formula for my straight line. But my slope is going to be 0.930. Okay, so it's y is equal, I'm going to use y is equal to mx plus b. The slope is this times the rate of unemployment is going to influence what the murder rate is, 0.93. So let me go back up here to the murder rate and poverty. Okay, the slope on this line was 0.36. So it seems like a 1% increase in the unemployment rate will have a bigger impact, increase the murder rate more than a 1% increase in the poverty rate. Although it's not as consistent, it's not as consistent and reliable a measure of it. But now we can see there's more than one factor here that's influencing the uh, 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 murder rate. So wouldn't it be really nice if we could write another formula here where y is equal to a slope, b0, plus b times the value of x, let's say that would be our poverty rate, right? This would represent our slope due to our poverty rate. I'll call that b1. But now let's also include the unemployment rate as a factor, b2 times x, right? And so on and so forth. Maybe even some other stuff like education level, b3 times x. Well, what's happening here is that when we're looking at simple linear regression, we're only looking at how one factor affects the predicted variable, the dependent variable, the y that we're interested in. However, there's many variables that might impact it. And it would be really nice if we could put together a formula that actually represents those many different variables. In fact, that's the difference between linear regression, simple linear regression, and multiple linear regression. We're going to talk about that on Monday. Okay, multiple linear regression. Again, if I go back here, if I want to actually, as soon as I did this, because I didn't turn it off, analyze regression linear, you may have noticed that in the save, it's still calculating the unstandardized values, the predicted values that are based on each state, and it's calculating the residuals as well. So if we go back to the data view, we'll see those values again as well. Oh, let me get to the data window. Here we go. There they are. Those are the predicted values for the murder rate and the residual values based on the formula that we created based on the line that best represents the association between the unemployment rate and the murder rate. Let me try another one. Analyze. I'm just going to go straight to regression here. Linear. Okay, and instead of unemployment, let's take a look at the percentage or the rate of single parent homes and see what kind of association that has. Okay, well, let's take a look at that one. Okay, so the R value is 0.677. Wow, there's really a strong association there. R squared is 0.459. Almost 50% of the variability in the murder rate is associated with the rate of single parent homes. Let's actually take a look at that data graphically. Okay. Now, single parent homes could be dependent on a lot of other things. In other words, a lot of confounders here. Could be a lot of single parent homes because they're of high poverty levels, could be single parent homes for many, many other reasons that might be associated with these other variables. But it's interesting that we would come across this kind of relationship. Let's put single parent homes in here and see how good a predictor that is. Well, wow, that looks like a lot better association than the ones that we saw before, we can actually see a much stronger correlation here, can't we? Okay, even graphically, even just looking at it graphically. And a large percentage of the variability in the murder rate, a large amount of that is predicted by the percentage of single family homes in the different states. Okay, again, this is another factor. If we could combine this with the poverty rate, with the rate of education, with the unemployment rate, and now with the rate of single parent homes, it would give us a window, a much more accurate window onto how these different factors combine, and give us a formula where if we had somewhere where we didn't know the murder rate, that we could use this to predict what the murder rate might likely be, given the other factors that we know about. The other value here is that the slope of this line tells you if you change the x value this much, this is how much the y value changes. What are we interested in controlling here? We're interested in controlling the murder rate, right? So if we know that the poverty rate has a flat slope, not much of a slope, that kind of tells us that a big change in the poverty rate only makes a small change in the murder rate. But on the other hand, the rate of single parent homes, a small change in the percentage of single family homes makes a big change in the murder rate. So this is not so easy a situation to address from a public health standpoint, because we really can't control the percentage of single parent homes too much, right? But if you can imagine this with other variables that you have more control over, drug treatments, interventions, training, and so on and so forth, you can compare different interventions, different training issues, different drug treatments, different exposures. You can choose the ones that are going to have the biggest impact, so that you can place your public health money, your public health effort. You can focus it on the variables that you can impact, that will make the biggest change in what you're trying to control. In this case, it's the murder rate. In other cases, it might be other stuff. Okay, so let's take a look at another data set. Okay, so in each one of these cases, we're going through the same steps here, right? I'm going to open a new data set. Okay, open data. Okay, let's see. I'm not sure that this is two numerical variables. Is it numerical? Nope, that's categorical data. Okay, that's not going to help me. Open data. Okay, I was staying away from that one. Slugging. Did I have another one here? Okay. Oh, let me open that one. I think I might have assigned this one in the homework. I'm not sure. Okay, so I think in the homework, I was asking you to compare BMI and insulin sensitivity, right? To determine how much BMI impacts insulin sensitivity. Okay, maybe for the moment, I'm going to leave that for you to determine. In other words, which of these, let me ask you something. BMI and insulin sensitivity, which one would be the independent variable? Which one would be the dependent? Which one here, BMI or insulin sensitivity, which of those is the independent variable? In other words, the predictor variable that you would use to predict the other. BMI, good, excellent. And which one is the dependent variable? Well, obviously the insulin sensitivity, that IS, is the predicted variable, or the result variable, or dependent variable. Okay, in this case, I'm going to leave that up to you guys, because that's, I think, what we use in the homework. In this case, I'm going to examine age and BMI. And in my case, I think age may have an impact. Obviously, high BMI is not going to make you older by itself, right? But age may impact your BMI, because maybe as you get older, you gain weight. Take my word for it. It happens to all of us. It happens to the best of us. At any rate, so I'm going to go analyze. I'm going to first I'm going to take a look at this graphically, see if there looks like an association. Okay, and I'm going to move BMI into my result variable and age into my predictor variable. Click OK. Let's see what our graph looks like. And boy, it doesn't look like it looks like a little cloud there, but I think maybe there is an association there. It's buried in there somewhere, I think. Okay, not a very good one, right? Age, I guess, I guess, I guess I was wrong. Age is not the biggest predictor of BMI. There are a lot of other factors going to predict what your BMI is. And I don't have to tell you that because, a lot of younger people have high BMIs. A lot of older people may have low BMI. So maybe I was a little bit rash in suggesting age was an important factor here. Obviously, only age only accounts for 5% of the variability in body mass index. So this didn't happen to be a very good option for us. Let me go finish this out and see. Let's go ahead and do our analysis. Let's do our correlation. Okay, age and BMI. Hopefully, with insulin sensitivity, get a more interesting result. Okay, and we can see that the correlation coefficient is 0.226, and our significance is high, so it's not statistically significant, right? So we have a low but not trivial correlation between age and BMI. There is some correlation, not very much of one, but we really can't say it's different from zero because our significance is not, our p-value is not less than 0.05. So it's an interesting result, but we can't, we really should stop at that, but I'm not gonna, I wanna go through the exercise. I'm gonna go to regression linear, and I'm gonna have it give me that formula, that straight line, the formula for this straight line, which represents the relationship between age and BMI. Not gonna be a very good predictor, we know that now. Age into independent variables, BMI into dependent variables, and I'm gonna click OK. And based on this result, again, we get the same result up here, r and r squared. Okay, based on this result, our formula for the best fit line is going to be y is equal to 0.006x plus 22.35. Right. Well, what is that? What is that formula again? Age represents. This is the slope of the line. This is the y-intercept of the line. So our formula, you could put the age into our formula and try and use it to predict what the person's BMI would be. Would it be a very good predictor? No, it wouldn't be a very good predictor in this case because our correlation is not only is our correlation not great, but our R square is very low and it isn't even statistically significant. Okay, so insulin sensitivity is a better measurement. And keep in mind when you do the homework, don't use the variable insulin. Use insulin sensitivity, when you give that a try. Okay, so I'm gonna call it a night. You guys, you can go back over the lecture. Don't worry about the derivations, the mathematical derivations that Levi used to calculate R squared, okay, or the actual formulas that he used to calculate what the value of R and R squared are equal to. It's good enough for us, for our purposes, to use SPSS to calculate the correlation coefficient R and to just square that to get R squared, to get a measure of how much of the one variable predicts the other variable. Right, so that's good enough for us. We at our stage don't need to do that calculation from the derivation that he did. Okay, so and if you do go back and listen to that, remember you can skip over the first 15, 20 minutes where he goes through some housekeeping and stuff like that, save yourself some time. Okay, any questions right now? Do you see how correlation and regression are useful tools to help us understand how two numerical variables are associated? Not only that, but we then wind up with a formula that we can use to predict a dependent variable based on what an independent variable is. And we can predict how we could affect the result variable based on how we modify the predictor variable. In other words, where we want to put, if we put our money in reducing this, what kind of effect that we can, reducing this predictor variable or increasing this predictor variable, what kind of effect that would have on the dependent variable, on the thing that we want to control. Okay, so take again, take a look at this, or take a look at the homeworks. I think they should be available now, and I think I corrected any issues that there was with the way it displays or anything like that. Try and stick with Firefox when you're working on Blackboard for the time being until they work things out with ICIT. And try and pick a day out on Monday or Wednesday next week when you want to show up. And if any of you want to attempt a project, please try and get in touch with me by Thursday night and the day. If I'm only going to be able to respond to you on Friday, you won't be available over the weekend, or by Friday night, end of day, if I'm going to be able to reach you by email over the weekend. And you don't have to tell me in advance whether you're showing up on Monday or Wednesday, unless you're presenting. If you're presenting, it will help me out a great deal if I know which day you're presenting at. And we have a bunch of nice, interesting data sets and stuff that we'll be able to work on Monday and really start to put ourselves into situations where somebody might throw data at us, and we will sit there and figure out, well, what kind of data is this? What statistical test is appropriate for this data? And how do I go ahead and use SPSS to actually do that? So I think that's really going to help us out quite a bit in terms of like applying this stuff in the future. Okay, so have a good night, guys, and I'll see you guys on Monday or Wednesday, one or the other. Take care, guys. Bye.